Alright, welcome back to the last little lesson for Chem 20 and of course for the stoichiometry unit. So this right here, like I said in the previous video, this is more of a theoretical kind of stance on titration curves. Now, if we did have a chance, I know I do have a lab where we actually plot one of these here, so the acid-base titration curves. But either way, we're just going to look at them at a pure theoretical standpoint and kind of figure out how they would actually look. So of course we know titrations are used to determine the concentration of things. So if you remember, there's a relationship between concentration of hydronium and hydroxide in pH and pOH. So we can also use titrations to determine the pH at the endpoint of an acid-base reaction as well. So of course, if you had pH meters and stuff like that, the information of titration can be plotted on a graph. Buffer regions can be analyzed. This is Chem 30 stuff, and stoichiometric calculations can be performed as well. But for the most part, we're just going to look at, how is it going to look? So what a pH curve or a titration curve, the reason why it's called a curve is because, as you're going to see soon, the graph kind of curves in a way. So what this is just a graph showing the continuous change in pH during an acid-base reaction or an acid-base titration. So a pH curve graphs the pH of the reaction on the y-axis and the volume of the titrant added on the x-axis. Now the endpoint, as we stated for these titration analysis, comes from a color change of an indicator. Now there's a bunch of different indicators that we've seen before, so it's hard to know what indicator that you need to use for a titration, or hard to know what the endpoint is going to be. So the endpoint is when the reaction's gone to completion. Now this is normally indicated by a color change or the steepest point on a graph. So now there's two different ways to indicate an endpoint. So if you knew what indicator to use, you can look at the indicator color changed. Or if we had this graph, we look for the steepest or the most vertical region on the graph, and that's how we can tell what the endpoint is. Now the equivalence point is, this is the same, the volume of titrant required for the reaction to go to completion or to reach the endpoint. Now when we are interpreting our pH curves, there's only a few small things we actually get from this. So one of them, the pH of the original sample. Right, so that is if you had a pH meter stuck inside of the Erlenmeyer flask, even before you added any titrant, well, obviously whatever reading that pH meter would read, well, that is just the pH of our original sample. So if it's, below 7, we know our sample is acidic. If it's above 7, we know our acidic is basic. Now the endpoint and equivalence point are usually located at the midpoint, so halfway or the steepest drop in the plotted line. So after excess titrant has been added, the pH is going to start going towards the pH of the titrant. So we'll kind of look what that means now in a second when we actually look at some of the graphs. So of course, when we're doing some of these right here, you need to choose an appropriate titrant for a lot of these reactions. So depending on what our sample is, first of all, we need to determine if the sample is an acid or a base, right? So you can do that with litmus paper, you can do that with a pH meter. So if the sample is acid, whether it's strong or weak, the titrant needs to be a strong base, specifically monoprotic base, such as sodium hydroxide or potassium hydroxide. If the sample is a base, whether it's strong or weak, the titrant needs to be hydrochloric acid. So that's strong monoprotic acid. So that just means hydrochloric is the best. We can also use hydrobromic, nitric, or hydroiodic. We stay clear of sulfuric acid because sulfuric acid, as we know, is H2SO4. It has 2 hydrogens. So we try to stay clear of that, right? We try to stick with these single hydrogen acids. Now, how a titration curve will look, let's get this. So neutralized, when we're talking about these reactions, the general meaning is bringing the pH closer to 7. That's it. So how these curves actually look, so when we look at a general acid-base titration, we have pH and volume right here. So we can tell right here, so the pH starting, so this is the pH of our sample, And as we start adding our titrant, and this is of course volume of titrant added, we can tell that it starts going up a little bit. Then we have the steepest portion right here, and right here in the middle, this is the endpoint. And then as the endpoint's done, right here we start getting close to the pH of our titrant. Because once the reaction is complete, all we're doing is just adding excess titrant. So that's why once we get this steepest portion right here, we know the reaction is complete. There's nothing left. So up here's the pH of the titrant. So same thing with our other one. Now we can tell right at the beginning, it's pH of our sample. Now in this case right here, we can tell our sample is a base. Right here is our end point, because it's the steepest portion, and down at the bottom, pH of titrant. So how do we always figure out what indicator we need to use for these reactions? So if we never knew what indicator we could use, we can always graph this and figure out what the endpoint would be, and of course the volume at the endpoint, and we can use that for calculations. Now, if we wanted to choose an indicator, the appropriate indicator will completely change color within the steepest portion of our pH curve. So that means that any indicator that will change color within this pH range in these steepest portions will be a good indicator for the reaction. So that means some indicators, like if you go back and look at some of your indicators, so the ones that are extremely acidic or extremely basic, like, you know, methyl violet only changes from 0 to 1.6, right? So that would be a bad indicator for a particular reaction. So you'll notice all the endpoints are around a pH of 7. So when we look at a lot of our best indicators, so something within that steepest portion, you know, we're kind of looking at kind of these indicators right here. So in the middle of our chart, right? Bromocresol green, methyl red, chlorophenol red, bromothymol blue, phenol red, phenolphthalein. These are all really good indicators, because if you look at those types of graphs, wrong thing, right? You know, you can tell that the pH range will be somewhere in here. Right? Obviously, you don't have all the pHs, so we don't know, but either way, that's kind of what we look for. Okay, so for some reason, the last page just did not want to load on, so just hold on once. I'll see if I can get this working. Alright, so I got that fixed. This is what the last page looks like. So basically all it is, like, just theoretically, obviously we don't have the numbers here, so it's completely label an acid-base titration pH if our sample is hydrochloric acid and our titrant is sodium hydroxide. So we know if our sample, this is an acid, right, so the pH should be low, and that's starting, right? So if we had a general Right, so just a general graph that looks something like this. So if we know our sample is an acid, so it needs to start below 7, so somewhere down here, right? So as we add the volume of the titrant, if you know how the previous graphs kind of look, the pH changes ever so slightly. When the reaction is done, we get a very steep portion going up, and then it kind of tapers off and goes up here, right? Where we know the end point is always going to be right at 7. The pH of our sample is at the beginning, and of course pH of titrant is always at the end. And that's all we can really tell from these graphs, is pH of the sample and the titrant, the equivalence point or the end point. That's right at the end of the reaction. Of course, for these here, it's always at a pH of 7. So that's kind of all we just kind of go over with these titration curves, is just kind of giving you light on we can actually plot these things if you have the proper equipment, which if we're in a lab setting, we would have the proper equipment to kind of do this. And of course you can pull information from this as well. And if you were given one of these here, and specifically what volume was actually used, if you knew some concentrations of either the sample or the titrant, we can use the volume of our titrant reacted right here to use our stoichiometry calculations. And that is it for the stoichiometry unit and Chem 20. So please work through your workbooks. If all possible, of course, there's only going to be one more assignment in this student assignment based on this. There will be no final this year due to the circumstances, but either way, make sure to continue working, and I'll see you guys for the last online help session as well at the end of this week. All right, see you guys later.